Welcome to Data Skeptic Pilot Season. I'm trying out a few new themes for the show as we transition out of Data Skeptic consensus and into whatever comes next. This is one of probably two more we're going to do before I ask everyone to vote, so check out the recent run we've had and form your opinions. Today's submitted for your approval, Data Skeptic Time Series. A delightfully broad topic. Today in particular, what we're going to get into is outlier detection, or more specifically, fairness-aware outlier detection. After all, what does it mean to detect an outlier? To find something unusual, to find a minority class. And I mean that in the machine learning sense of that word. But of course, it could be used even inadvertently in a damaging way. So it's great to see things like the fairness-aware outlier detection methods discussed in the paper we're going to go over today.
Hi, my name is Shubhranshu, and I'm a PhD student in machine learning and public policy at Carnegie Mellon University. My research basically focuses on pattern mining and anomaly detection in decision support systems.
I think a lot of people have a vague conception of what anomaly detection is. You're welcome to give a formal definition or an informal one, but to you, what is anomaly detection?
Anomaly detection is typically, I'll give you an informal definition or informal sense of what anomaly detection is. So anomaly is defined as anything which deviates from the normal. So as you can see, the definition of normal is again dependent on the application or the domain where you are applying some concepts and so on. So for example, if you are looking at a classroom, right? So if you're looking at undergraduate classroom and if you're just recording ages of the people present in a classroom, all the students typically would have an age range between say 18 and 21. And maybe professor has an age range between 35 plus or something. I'm just making this up, right? So in that sense, the normal is defined because we are only recording age. So in that sense, normal is defined by maybe the ages around 20. So in that sense, the teacher would be an anomaly in that sense because the teacher's age, his or her age is way different from the normal, right? So in that sense, the teacher would be anomaly in this case. So essentially, anomaly detection is a field which tries to find unusual activity or unusual observations in a given domain. And that's what anomaly detection deals with. And since it's about finding unusual things, you typically find applications of anomaly detection, intrusion detection, say fraud detection, or even in medical domains like say epileptic seizure detection and so on.
I imagine there's a broad range of different methodologies one could try, maybe some unsupervised for sure, possibly some supervised. What does the typical landscape and toolbox look like?
So anomaly detection by design is a ranking problem wherein it's an unsupervised task where given a collection of objects, you assign some score to each of these objects in a rank order fashion where the object which receives highest score or lowest score, or typically highest score, is an anomalous point or is most anomalous compared to the group of or the collection of points that you have. So anomaly detection is typically a ranking task where you rank most anomalous or most unusual point up to most normal point and so on. So since anomaly detection is about unusual activity detection, typically most of the problems fall into unsupervised learning domain where you don't have a priori knowledge of class labels. But there could be certain domains where you may have supervised anomaly detection, but then supervised anomaly detection would be very close to supervised learning problems with skewed class distribution. So skewed here, I mean by that, there would be only a few examples of unusual activity and rest everything would be usual activity. So you could solve those problems by using supervised problems, but typically then you will have to employ techniques to deal with high skewness of the data because in any system, number of anomalies would be somewhere around 0.1% or even less than that. And that's very hard to train with when you have supervised learning problems. So I think people typically utilize unsupervised methods, which could be either tree-based or density-based and so on.
Yeah, anything with outlier detection is inherently going to have that class imbalance problem where you have so few examples of the minority, usually interesting class. Like fraud detection is a great example that you'd mentioned. The people committing fraud are not going to be so kind as to reveal their nature. They're going to try and trick you. So it's got to be something new and novel. You touched on a couple other domains, and one that caught my attention was healthcare. I was previously not aware of any real concrete use cases for anomaly detection and outlier detection in healthcare. Could you go into a little bit more detail on how we benefit from the use cases there?
I'll just give you an example of one of the problems where I'm working on seizure detection in a medical domain. So typically, like a human brain would operate between certain ranges of voltages. For each person, that normal range would differ, but typically it would exhibit certain behavior during normal periods. But during seizures, what happens is like seizure is essentially like either a very high activity in one part of the brain and almost no activity on the part of the brain and so on. It could be either way. Typically, very high activity or very high frequency activity going on in the brain. So in that sense, in that landscape, so if you're only looking at voltages, simplest case, so you have a timeline of if you are observing a person over time and you see like typical voltages are say some 1 microvolt or 2 microvolt or something like that. And suddenly you see spikes of like 10 microvolts, 5 microvolts, or even more than that. So in that sense, you have observed a voltage which deviates from your normal observations, which is around 2 microvolts or something. So in that sense, you could easily detect seizures. Although in real world applications, it's not that straightforward, but the underlying idea is still the same.
So in a case like that, it feels to me like it's all upside, that these are, additional automated steps that could benefit healthcare and doctors and maybe, raise attention to catch things earlier or expand our ability to check patients. So all positive things for sure. Even in fraud detection, I don't necessarily see a downside because if the company makes a mistake and I'm a legitimate user and they turn away my business, I guess I can go to a competitor. But then I started thinking about what about anomaly detection in security cases? Lots of good examples. But I would hate to think that at the airport, tall people and maybe redheaded people and just rarer minority people would be flagged because they're outliers compared to the general public. How can we introduce some notions of fairness into these ideas?
Anomaly detection is about detecting unusualness, but then unusualness in the statistical terms is basically low density region in a feature space. Right. So what happens is that when you give an example of airport security and people with different types of attire or hairstyles and so on, any person which has a different kind of hairstyle would stand out in this feature space. And standing out means that it will be unlike any other point, which means it will have low density. And low density is statistically low density is our anomaly by definition. So in that case, like if say, for example, if a person has a raised collar of his or her jacket, and we will flag them as an anomalous person, but this raised collar, if that doesn't correlate with the actual harm that that person can do, then this system then becomes unfair in that sense, unfair with respect to minorities. So recently we worked on introducing notions of fairness into outlier detection, which is very challenging because of two aspects. One is like in supervised learning scenarios, there have been numerous fairness metrics that have been proposed. So it's very hard to figure out which one could be applicable to outlier detection. So then we thought about introducing fairness into outlier detection. The first problem that comes into outlier detection, introducing fairness notion to outlier detection, is availability of so many choices for notions of fairness and their formulations. Most of these formulations come from supervised learning problems, which have received unusual focus in terms of fairness in machine learning, while there is like almost non-existent work in fairness in outlier detection. So the problem becomes challenging as to which notion of fairness would work best for outlier detection. The other thing is like, as we talked about outlier detection, is we only have unlabeled data, or it's an unsupervised learning problem. So absence of ground truth outlier labels makes this problem even harder to even post-processing or some sort of processing that many of these supervised fairness algorithms apply. Right. So to that end, in our recent work, which is called as FAIROD, we have first of all designed desiderator to cater to this problem of fair outlier detection. We also give a formalized problem definition for that. And then we introduce a fairness criterion that could be incorporated into an outlier detection model.
When I think about your example of a classification case, so not the unsupervised case you're working on, it feels a little easier in some sense to me because intuitively, if I look at my model after the fact, I can test it and say, well, if it's a loan approval process, you'd expect the same rates across different groups, male versus female, left-handed versus right-handed. Those should not be criteria that help you decide the outcome of a loan. So if it shows up, we can measure it. As you were stating, there's no ground truth, so we need other criteria. What do you lean into to find something useful here?
So then when we looked at different notions of fairness, the first and foremost that comes to our analysis was something called as statistical parity. So statistical parity is talking about the model's outcome should be independent of your membership to any group. So here, this statistical parity, as we know it, depends on the outcome of the model. It doesn't depend on the ground truth. So essentially all it says is statistical parity is talking about like I should match the ratios of number of people assigned label 1. So if I have flagged say 10 people, right? In total 10 people I have flagged as anomalous. And there you have two groups with population 80% and 20% divide. Then I should have in those 10 flagged 2 from the minority group and 8 from the majority group, so as to maintain the ratio of outliers. So that's what statistical parity is. So this notion of fairness doesn't directly depend on the ground truth, and which is where we include this notion of fairness into our model. Yeah, I would refer you to the details if you want to look into details to the paper FAIROD by us, Fairness Aware Outlier Detection, for more comprehensive understanding of what's going on there.
Yeah, we should drop the name of the paper again. It's FAIROD, Fairness Aware Outlier Detection. I'll have links in the show notes. Great resource. Enjoyed reading through it and picking up a lot of the ideas you guys have presented here. What was the state of the research before you came to it? Were you and your co-authors the first to take a look at the unsupervised case?
There was one work which was specifically into this direction, but the literature that looked into this direction, that was primarily focused on one particular outlier detector. And even there, what it was doing is there is some notion of disparate treatment. So disparate treatment essentially tells you that when the decision time arrives, your model will ask you your membership to your group, right? So then essentially your model will score you differently based on your membership to a group. So essentially you are doing a disparate treatment based on your membership. So the models that authors have suggested, that suffers from this particular problem. And if you know, like in many of the domains, especially in US, so for example, banking, loans, employment, asking for your membership to a group such as your racial information or say income information is illegal. I mean, it's like people are protected under law to not disclose those information. So if your model would have disparate treatment, then that model would become useless in such domains. But there hasn't been any other work apart from this in this domain as such. So this is like ours is like first work in the sense that first work to give you a desiderata to design your own outlier detector. And following our own desiderata, we design an algorithm, outlier detection algorithm, which is shown to be doing fairly well on synthetic as well as real world applications.
Do you have to have some notion of the context for the group in order to do the statistical parity? Can I just use columns X, Y, and Z, or do I have to really do a selection process of what is a potentially protected field or property of the values I have?
Right. So typically the protected field is something that is protected by law or something that is personally identifiable, right? So for example, you have to pre-specify what are your protected fields. In general, there could be ways to get that from the data, but I'm not aware of that. Typically people have to pre-assign or have to know which field are being used as protected attribute, or protected attribute is the attribute which decides your belongingness to a group, majority or minority. Typically, race, gender, income, age, these fall under this protected attributes that people utilize for handling the notion of fairness in any algorithm.
There could be cases where you want to apply these techniques and different outliers will be found through the methodology, right? That's how it's kind of designed. The question then becomes, are these true outliers? I don't imagine you'd say, a bank should just automatically decline a loan, or maybe it should if they do high volumes of them or something, but probably a researcher would take this as one consideration in a step. Or how do you see this fitting into the workflow of different projects and research going on?
Typically, the use of outlier detection is for two things. One is for attention drawing to suspicious observations. The other is like you could place some trust in your algorithm and you could create labeled data for your downstream applications, and which you could use then to learn a classifier for flagging out like whether to give out loan or not. So in that sense, if your outlier detector kind of is being unfair towards a minority group, then that would manifest even worse in the classifiers down the line. That has few reasons why that happens. So one thing is there is a feedback loop associated. So like let's take an example. In a city, if there is a lot of law enforcement officers assigned to certain different areas based on some reasoning and whatever. So maybe that comes from our initial outlier detector label. So if outlier detector say these regions seem to have high crime rates because these regions seem outlying, then you will place your law enforcement officers in those areas. But then what happens is that as time progresses in subsequent iterations, what you will notice is that where you had heavily deployment of law enforcement officers, they will start to report more more incidents because you have every geographical area is kind of covered with them. And there could be a large part of areas where you have very few law enforcement officers where many of these illegal activities may go unnoticed. So what happens here is that then in the subsequent iterations, the data that you are generating from the initial deployment, then you are basically are biased against a particular geographical area more and more and more. So that feedback loop could be a result of this biased outlier detector. Such problems may arise if we do not handle fairness in the outlier detection in general.
Thanks to this week's sponsor, LinkedIn Jobs. Small businesses have always shown an incredible ability to adapt, innovate, and survive, even more so this past year. Now, another way you can adapt and grow is by finding the right people to help grow your business. LinkedIn Jobs helps you do that for free. They provide you an all-in concierge-style web interface. Log in, post your job, which again is free. You'll start getting candidates immediately, quality candidates. Where better a place to learn about them than right there on LinkedIn? Message and connect all in one seamless interface. Get started by posting your job and reach LinkedIn's network of 740 million professionals. Fill out targeted screening questions to get your role in front of the most qualified candidates with the experience, skill, and motivation you need. When you need an exceptional professional to join your team, start your search at linkedin.com/dataskeptic. Your first post is free. You've got nothing to lose. Head over to linkedin.com/dataskeptic. Terms and conditions apply. Well, I've focused in on most of my questions on this notion of statistical parity because I feel like that's one of the meatiest aspects of the contribution, but there are other proposed desiderata coming from the paper. Could we do maybe a quick outline or some deep dives if you're interested on the other properties that you're proposing in the framework?
I would like to say the statistical parity is not the meatiest of this proposed work because statistical parity has been established earlier as well. Even, given the nature of the problem, it's an unsupervised problem. So statistical parity fits this problem that we have at hand, which is outlier detection. But then even statistical parity suffers from a notion that we call in our paper as laziness, which is it has been referred earlier also in literature as laziness, where what happens is that statistical parity, all it does is it cares about matching the fractions of your flag observations to their protected groups, right? So it could do so in such a way that it would flag, say, actual outliers from minority groups, right? And when it comes to majority groups, you could just randomly sample some observations and say, okay, these are outliers. So in that sense, you would always be able to match the fractions, but then you will not be actually flagging the real outliers from majority group in that sense. Statistical parity suffers from that problem, which is why we require some additional constraints to this problem, and which is where we introduce our desiderata. So our desiderata is basically a 5 tuple, where the first thing is like for any outlier detector, it should be effective at detecting, right? So this desiderata has nothing to do with fairness. It's just talking about the effectiveness of an outlier detector. So what do we mean by that is basically what we're saying is like the precision of the detector should be better than random, right? So essentially, if I flag, say, 10 examples, 10 observations as outliers, probability that these flagged outliers are true outliers, that should be greater than your base rate. So base rate here is basically the proportion of your data which is outlier. So if your proportion of data is like zero point 0.1, so if your 0.1% of the data is outlier, then your precision should be larger than that. Then only it makes sense to do outlier detection. Otherwise, you would just randomly sample some people and then you will find who would represent as outliers and so on. Right? So this is just talking about the effectiveness.
Yeah, necessary but not sufficient. So what else?
Right. Yeah. Next thing is we also require treatment parity. So treatment parity is, as I explained earlier, that for in the domains like loans and employment, one should not be asked to furnish their protected attribute group membership. The outlier detector should exhibit non-disparate treatment in the sense that the outcome that outlier detector gives you, whether you furnish your membership or whether you not furnish your membership, the output should be the same. So essentially, it does not require a person or an observation to reveal its membership to protected group. So that's another criteria that must be satisfied in outlier detection. Then we think about statistical parity. So given that it's effective, it has treatment parity, then we talk about statistical parity, which I think we have already covered in detail to some extent, like where what we want is that flag rate across two groups should be same. So essentially we are flagging. Whenever I say flag, basically flagging means that I'm saying this observation is outlier. So that is flagging. So assigning a label 1 or assigning a label as anomaly is flagging. So equal proportions from majority and minority groups should be flagged. That's what statistical parity is talking about, but it suffers from this issue of randomly flagging some people from majority group, but from minority group you flag true outliers. In that sense, your model is always biased against minority group in some sense. So given this, what we need to do is that to deal with this issue of statistical parity's laziness, in the sense where majority group could be randomly sampled, what we need to introduce something we call as group fidelity, which is a property where we want that true outlier should be equally likely to be assigned higher scores, regardless of their membership to the group that the points belong to. As you see from this definition, it immediately tries to address the shortcoming of statistical parity by introducing this notion that true outliers should be assigned higher scores. Of course, we don't know what true outliers are. So from this definition, it seems that, okay, we need to have ground truth available. So typically, this definition is also known as equality of opportunity in supervised fairness problems, but we do not have available labels associated with that. So in this paper, what we do is we propose an approximation to group fidelity, where what we say is that instead of looking at ground truth labels, since outlier detection is a ranking problem, what we say is that we should be able to preserve the group level ranks from the base model. So base model would be a model which does not incorporate any fairness criteria. So what we are saying is a base model would typically be effective at detection, but it discards any notion of any group membership and so on. So it may be biased against minority group and so on. But what we hypothesize is that if we look within group, then even the base model within group would typically rate the more outlying points as assign more outlying points as high scores within each group. So we try to preserve this notion that we have for from the base detector into this criterion. So essentially what we're saying is the fair detector should preserve this group rank order. So that way, what we will do is even for the majority group, we should be able to flag only those individuals who should be higher in the rank for the within their group. and essentially giving rise to a rank list which is fair enough or fairer or approaching fairness. The other thing is like one desideratum that we propose but we cannot enforce or we could not enforce was something like base rate preservation. So what we are saying is that base rate is like your probability of being outlier given you belong to majority group. So what we say is that in the fair outlier detection, we should be able to preserve this base rate in the flagged population that we have. So the flagged population should be representative of true population that we have. So flagged population are the individuals that we flag as being outlier or not being outlier, at least flag for doing further policing or further investigation. That should be representative of the true population because down the stream classifier should not be biased in the sense that they should learn from a sample that represents true population. But as we show via various proofs that base rate preservation is not possible, at least was not achievable within our limits. So that is something we cannot maybe preserve at this point, but at least, achieve statistical parity, and we can address the shortcomings of statistical parity by introducing this notion of group fidelity. So the meat of the work in this sense is the combination of statistical parity with group fidelity. And the other thing is basically this desideratum for designing any outlier detection now further down the road. Like if anybody wants to design a fair outlier detector, they can get up this desiderata and they can try to ensure that each one of these desideratum is being enforced in their detection algorithm.
And these different properties, even though it may not be obvious from our audio conversation where they're intuitive to the mind, they also have great statistical forms. You can translate these into their mathematical versions, which means we can use them in machine learning in some way. Can you talk a little bit about the experiments you guys did and how this is all implemented?
Each of these properties that I mentioned, each of these properties are essentially has a statistical identity associated with that, which I think I will refer our listeners to read the papers. That way it will be much better. Now, once we established the notions of fairness and the criterions that a fair outlier detection should include, then what we do is to demonstrate the effectiveness of this, we start with a very simple outlier detector based on like reconstruction based outlier detector, which is what we do is we use a deep autoencoder. So autoencoder is you want to reconstruct the input features from a reduced dimension representation essentially. So if you are not able to reconstruct back a certain example, maybe that example deviates from the normal, and then in that sense you could flag those examples as outliers. So what we do is we start with very simple or deep autoencoder as our base outlier detector, which does not include any notion of fairness. And then we want to introduce notion of fairness into such outlier detector. The reason for choosing this outlier detector was basically it is easy to optimize. It's not easy to optimize. I mean to say that it can be optimized to some extent, and any optimizable outlier detection framework could work with this because the notions of fairness that we introduce, they are statistical quantities which can be turned into loss functions. And if you have any outlier detection algorithm which has a defined loss function, then all you need to do is you need to include the notions of fairness, the loss associated with those to your existing outlier detection loss to learn your model or learn the parameters of your model.
Gotcha. So FAIROD is not just like a way to score or give a report card. This is like a regularization technique too. Is that right?
Yes. So it involves to some extent a regularization. So it takes a base loss function and it introduces a regularization with respect to the fairness constraints that we talked about.
Gotcha. So we want a result that's not only useful, but also fair. Makes sense.
Yes.
And let's get into some of the experiments. What sort of data set and test can you run to evaluate the quality of these results?
To first of all, like when we do experiments in such new things, we don't really have benchmark data sets, like where we just evaluate a given metric and then you were done with that, right? So here to demonstrate the effectiveness, we started with a very simple synthetic data, two-dimensional data, where what we had is like we had features are like two dimensions, such a way that you have a feature which is highly correlated with true outlierness. So in this, since it's synthetic, I will also have ground truth labels to evaluate the final result of the model. So here we had like two features. In one case, it's highly correlated with the output, which is like ground truth outlier. And other case, the other feature is independent of the output. And then we have another data set, synthetic data set, two-dimensional, where we have features which are partially correlated with both the thing, which is group membership as well as the ground truth outlierness. And the other one, it was like one feature determines your group, directly correlated with the group. One feature directly determines your ground truth outlierness label. Although you don't know that, right? Your algorithm doesn't know that. To compare our experiments, the first thing we need to establish are like on what criterion do we want to evaluate our models. So the first thing is, since we are talking about fairness, we define fairness as basically the flag rate ratio, probability of being flagged given that you belong to a certain, so say majority group, and the flag rate ratio is the ratio of majority to minority of this probability, right? So we take that as fairness measure, and as you can see that for a fair outlier detector, this ratio should be close to 1. The other thing is, as I mentioned, like, so this basically captures your statistical parity that we talked about, right? If your model satisfies the statistical parity, then your fairness score should be close to 1. The other thing we talked about was the issue with the statistical parity was that it doesn't can randomly flag some people from majority group, right? So in that case, to measure that, what we do is we create an evaluation metric which is called as group fidelity, essentially as the way we designed it, right? So we are talking about like the group ranking should be preserved. So essentially for any ranking, evaluate any ranking, you could use NDCG scores, right? So we are looking at basically that NDCG score for majority group, NDCG score for the minority group, and we take harmonic mean of those to kind of compute this group fidelity. So harmonic mean typically tilts toward the lower number between the two. So if you have high group fidelity, that means that you are preserving the base ranking and so on. And so these are like the primary evaluation metric that we used. And then we tested our algorithm on like 4 data sets. I think these are like fairly popular data sets these days, like adult data set, credit default data set. These two are fairly popular in fairness related papers. The other two data sets that I used was one was abusive tweets. So I collected tweets from groups with a language as African American or mainstream. The African American dialect is encoding your racial dialect, and the goal was to find out outliers. So typically, your outliers, if you do not enforce fairness, then what happens is that typically you will flag out most of the African American tweets as outliers because they do not contain. So they are minority in number in first place, and the vocabulary used is different from the mainstream vocabulary. So how do you introduce fairness into such problems and so on? So these are data sets that we used, and then we compared our models with the base model itself, and we repurposed few of the pre-processing unsupervised fair representation learning methods as for doing outlier detection. So where we use those learned representations and we ran normal outlier detection on those learned representation to see if on a learned representation do we get a detector which could be fair, which passes on fairness from the unsupervised learning to the outlier detection and so on. And then typically what we observe is that on fairness axis, we would be across data sets, like including synthetic and the real world data set, we typically would be fairly close to fairness value equal to 1, which essentially tells that our method achieves statistical parity. When we compare with pre-processing based methods, although pre-processing based methods are also designed to honor statistical parity, but they did not learn the representation keeping detection in mind. So detection is a separate process from the learning representation part. And when we do a detection on this learned representation, what we noticed is that the statistical parity was not achieved on those methods. Like we have different types of methods over there, like reinforcement learning based methods, reweighting based methods, and so on. But then they typically would not achieve statistical parity because these methods would try to try to incorporate fairness independent of detection process, which is so in our method, since we introduce fairness notion as a integrated method, we typically outperform most of the competitors on the fairness task and so on. So other task was like looking at top K rank agreement and so on. So we observe that we also notice that the fair outlier detector, what you would expect. So you would expect that you have a ranking from rank list from an effective outlier detection. All you need to do is play around with this ranking in such a way that your top K ranking becomes fair, or fair in the sense that it obeys certain notions of fairness that you have introduced. So your rank list should not be drastically different. It will just be some other permutation of this rank list, right? Your fair rank list. So in that sense, we also, as I mentioned, a score called group fidelity, which measures how well are we preserving the group rankings. And again, based on our experiments, we show that here, I think our method will be little biased in the sense that our method has a component to preserve that ranking. So when we measure the NDCG, we typically outperform all other methods because none of the methods are preserving the base ranking that a base model would learn on a given data set. So essentially what we show in our data set is so in terms of notions of fairness, which is group fidelity and statistical parity, we achieve those and we are doing much better than competitors. And when it comes to effectiveness, we measure the effectiveness of our method with respect to base method, because base is kind of optimized for doing detection. And there we also notice that the performance, in terms of average precision or precision, doesn't deviate much from the base model, right? So, or it deviates least from the base model compared to any other competitor. So here competitors are not true competitors, they are pre-processing based methods, as I mentioned earlier. So in that sense, what we show is that by following our desiderata and by incorporating the notions of fairness that we have introduced, we are able to achieve a very nice balance between fairness as well as performance. In fact, one thing to note here is that in many of the machine learning papers, you would notice that with the notion of fairness introduced, you sometimes have to trade off performance. But in the case of outlier detection, what we observe is that's not always true. In fact, that's not, in most cases, what we see is that we improve the performance when we incorporate fairness. And the reason for that, as I mentioned earlier, was because we enforce that the top ranks from the majority groups should be aligned with the true outlierness. And hence, what we do is when we introduce fairness, we improve the top K ranking as well. When we introduce fairness with our group fidelity as well as statistical parity, what we have is we refine our top K rank so as to have a better performance sometimes. That's an interesting thing that you could take a look at in our paper as well.
Yeah, that's interesting. It's almost like a free lunch then, yeah?
Right. Yeah. So, in some sense, yes. Because as I said, when you introduce fairness, you push down the false positives.
Yeah, I think that's, even if for someone, not that there are people out there who don't care about fairness, but even if that's not your priority, you're getting a net benefit in this case then, which is interesting.
Yes, that's true. This will not always be the case because depending on how your top rank list is, right? But there may be cases where you will push down the false positives. So in one or two data sets, we observe that thing, and that's where we have a better performance over there. Just to clarify, it's not always the case. That's what I wanted to say.
Well, what's next for you in your research? Is this a step in one direction, or is this just part of your overall research interests?
It's part of my overall research interest because my research interests are mainly focused around anomaly detection for policy problems or social problems in general. So this fits in there. I typically work in medical as well as insurance domains. And the problems over there are of interest to society at large. So this particular fairness-based outlier detection also fits into that story where you want to have a fair outlier detector for doing insurance fraud claim, and so finding fraudulent insurance claims and so on. That kind of goes into the overall picture where my PhD has been focused on anomaly detection for societal problems. This definitely forms a big part of that.
Absolutely. Where can people follow you online?
Best way would be my website. If you just search my name, you should get there. I'm slowly getting active on Twitter, so you can look me up on Twitter.
Awesome. Well, I'll have a link to both in the show notes. Well, Shubhranshu, this was really great. Thank you so much for taking the time to come on and share your expertise.
Thank you so much, Kyle, for inviting me here. And I'm really happy to share my thoughts. And I'll also be happy to help you with any follow up questions that your listeners may have. Thanks.